Welcome back. This is video lecture 11.2, part 2. We are now back in chapter 11, and we're studying section 4, which is going to come back to the topic of torque, which, as you recall, was introduced initially in the previous chapter, chapter 10. And the way we described it there was that torque was a measure of the tendency of a force to cause rotation of a body about a fixed axis of rotation, like a door along the line of its hinges, or a cylindrical pulley along the axle through its center, or a wheel along the axle through its center. What we're going to do in this chapter, this section 4 of chapter 11, is extend that idea of torque a little bit. We're no longer going to require an extended axis of rotation, like the line along the hinges of a door, but we're going to recognize that a force can cause rotation about a single point. It doesn't have to be an extended axis, just a single point. And we want to calculate the tendency of the force to cause rotation about a point. And that's what we're talking about. We're talking about calculating torque about a point. I'm just going to tell you how we do it. I'm going to show you how this formula does give the same answer that we would get using the techniques of torque calculation in chapter 10. But I'm just going to start with the definition. And now you will see why I did video lecture part 1, where I went back to chapter 3 and talked about the vector product of two vectors, because that's what I'm going to need now. Here we go. Calculating torque about a point. Symbol for torque, remember, is still the Greek letter tau. And now we're going to recognize that torque, like force or any other vector quantity we learned, is a full-blown vector with a magnitude and a direction. And you calculate tau arrow about a point, by definition, by taking the vector product of the position vector that points from the specified point out to where the particle is, crossed into the force vector, R cross F. Vector product of R cross F. Note the order, R cross F. This is the definition of torque. But because it includes a vector product of two vectors, R and F, we have to be able to think and visualize three-dimensionally. Okay? All right, so torque is the result of the vector product, so-called the cross product, of position relative to a chosen point and force. So let's go right to pictures, okay? But again, we're going to have to think three-dimensionally. So our pictures are usually going to be 3D. So let's look at the first picture A down here on the left. We've got an X, Y, Z coordinate system. We're always going to have to figure out some way to try to represent 3D on a 2D drawing. So the way they did it in this picture is the XY plane has been drawn there kind of horizontal, shaded in green just so you can visualize it. And then the Z-axis is perpendicular to that XY plane, and in this case pointing up. And this picture is going to calculate the torque about the origin. So that's the point O, right there, the origin. Okay, in this picture, we have a particle. The particle is represented by that dot right there. That's an actual particle. It's at A. And that particle has a position vector R relative to point O that would be drawn from O out to where the particle is. Okay? There it is. That's R arrow. That's the position vector. And then someone is pushing or pulling on this particle, and at the moment we took that picture, the force on it from the push or the pull on the particle is that way. They've drawn it lying in the XY plane just to make the drawing a little bit easier to deal with. So there's F arrow. Okay, we've got a particle. It's got a certain position vector R drawn from O. And there's a force F. Notice how we drew F in the first drawing, anchored with its tail on the particle. That's the way I always recommend starting when you think about forces. Put the tail on the particle. Okay. Now the drawing also shows an angle labeled phi. It's what you get if you extend R. All right, it's right there. Okay? All right, so here we go. That's the picture showing the R and the F and the angle phi. How do I find first the magnitude of the torque using this new formula, R cross F? The same way I would have you do magnitude for any vector product based on the previous lecture. Okay? Magnitude of torque. Notice how I've denoted it. Tau arrow magnitude. You get it by taking the magnitude of the first vector, R, scalar multiplied by the magnitude of the second vector, F, scalar multiplied by the sine of the angle phi, which is the angle between R and F when they're drawn with a common tail. Well, maybe we better draw R and F with a common tail so we can be sure that we got this phi right. So now let's look at picture B, the second picture. Same scenario, xy plane shaded green, particles out there, particle A is out there, position vector R, force F, but now they've redrawn F with its tail at the origin so that it has a common tail with R. And sure enough, there's the angle between them, and it's the same angle as we have out here, phi. So, to calculate the magnitude of the torque, we need to know the magnitude of R, we need to know the magnitude of F, and we need somehow to be able to figure out that angle phi, or be given that angle phi, and then we take the sine of phi. But this picture shows some other things, mainly just to convince you that this new way of calculating torque, actually, we haven't really changed the rule from how we did it in chapter 10. Let me show you. Let's look at the rest of this picture B. Okay, let me go back to the original force, F, right there. This picture has taken that force and decomposed that force into two components. One component of F that's perpendicular to R, and the other component of F that's parallel to R. And focuses on the component of F that is perpendicular to R. Right there. Note from trig and that little right triangle that there's the angle phi right there, and F perp is magnitude F times sine phi. Magnitude F times sine phi. So in the formula over here, I could take the magnitude F sine phi part and just replace it with F perp. And then I get the formula that the magnitude of the torque is magnitude R times F perp. That was one of the alternative ways for calculating torque in chapter 10. And we're just showing you that this new way is equivalent to that, so that we haven't really changed what we're doing. But now let's look at one more picture, picture C. Same scenario, xy plane shaded green, particle A, position vector R, there's the force F. Okay? But now, let's take that force and extend it. Remember, that would be called the line of action of F. Now let's draw the moment arm, R perp. That's the perpendicular distance from the axis of rotation. Well, that's how we said it in chapter 10. Now we should say from the point O, the perpendicular distance from the point O to the line of action. Right there. That's R perp. Note that this angle right here is phi. So that R perp can be computed by taking magnitude R sine phi. So that if I go back now to my torque magnitude formula over here, and now I group magnitude R times sine phi together, that's R perp. and then I'm just multiply that by F magnitude. So I get yet another way to calculate the magnitude of the torque. Moment arm, R perp, times the magnitude of the force, which is how I did it in chapter 10. And again, I'm just showing you that this method over here for calculating the magnitude of the torque from the vector product, right here, is equivalent to the way we were doing it in chapter 10. Okay? All right, now all that is about getting the magnitude of the torque. Okay? Because the force in this scenario is wanting the position vector R that points from O to A to rotate about O. That's where the torque's coming from. We now have a new way to calculate the magnitude of that torque. What about the direction? Torque is a full-blown vector with a magnitude and a direction. How do we get the direction? Vector product, right-hand rule. Whenever you have a vector product, I want your brain immediately to think right-hand rule. So, as we said in the previous lecture, if you have a vector product of two vectors, the resultant of that vector product has two properties. One, it is perpendicular to the plane of the original two vectors, and its direction is given by the right-hand rule. Okay, so in our drawings here, A, B, and C, the plane of the original two vectors, R and F, is the xy plane, and that's why it's shaded green to help you visualize that. So R cross F must be perpendicular to the xy plane. That leaves you with only two possible directions for the torque. Perpendicular to the xy plane going straight up in this drawing, which would be plus z, or perpendicular to the xy plane straight down, which would be negative z. There's only two possibilities. Which is it? The right-hand rule gives us the answer. Okay? So the torque must be perpendicular to the plane containing R and F, and we use the right-hand rule. So let's take the first picture. Oh no, I'm going to change my mind. Let's take the second picture. Okay? All right, let's look at the second picture, B. All right, and look at the R as it's drawn, and the redrawn F with its common tail there with R. Both drawn with their tail at O. Okay, we use the right-hand rule, R cross F. So we extend fingers of our right hand and thumb of our right hand like we're going to hitchhike. We've got to have our fingers along R. So you're going to have to kind of do a little contortion here, because your fingers have to point along R, and your palm has to face F, so that you can push R on top of F, and your thumb points up. And so that's how the right-hand rule tells you that the torque, tau arrow, is along plus z for the given drawing here, with the R and the F as drawn. So they draw notice where they draw the torque vector. They draw it with its tail at O. Although you could draw it anywhere you want. You could draw it with its tail at A. Just make sure you draw it pointing along plus Z. Okay? All right, let me show you a Wiley Plus animation, which is going to put an R and an F for a particle, and we're going to put them both in the XY plane, like here, but it's going to show you just a 2D view. Let me show you that animation, because you'll also see this kind of a picture. Okay, so here we're looking down from above on the XY plane. It's shaded in a kind of a light brown color. And this animation is going to calculate torque on the particle. The particle is that red dot, which looks like it's sitting at coordinates x equals 2 meters, y equals 3 meters. And there's going to be a force, F, represented by the dark blue arrow, which by default has a magnitude 2 newtons and is pointing in plus x. It is drawn with its tail anchored on the particle. And we're going to calculate torques about point O, which is the origin. So there's another vector in light blue, a position vector R, that points from point O out to where the particle is. So those are our two vectors. There's the R vector. If you Want to, you can express it in unit vector notation. R arrow would be 2 meters times I hat plus 3 meters times j hat. And here's the F vector, the force that's acting on that particle. And that force is going to want to cause that position vector R to rotate about O. And that force vector is 2 newtons I hat. Okay? All right. The animation calculates the torque for us. Well, magnitude, and then it's going to give us the direction in a minute. But notice how it calculates the magnitude of the torque. Magnitude of R, magnitude of F, sine of the angle between them. Well, that's the same as this arc right here that you see in black. Turns out the magnitude of R is 3.61 meters. The magnitude of F is 2 newtons. And then this animation, with the information given, figures out the angle and takes the sine of it and tells us the final answer for the magnitude of the torque, 6 Newton times meter. All right, that's the magnitude. What's the direction of the torque? I would like you to try that for yourself, please. Feel free to pause the video. I want you to figure out for me the direction of the torque vector on this particle. Particle is the red dot, about the point O, which is down at the origin, and then come back. All right, did you use the right-hand rule? Did you take the fingers of your right hand and push R on top of F? Did you realize that the direction of the torque has to be perpendicular to this XY plane? So there are only two possibilities, either straight out towards us, that'd be plus Z, or straight away from us into the screen, that'd be negative Z. So you have to imagine drawing R and F with a common tail. One way to imagine that is to imagine sliding the R straight out along that black dashed line until it has a common tail with F. And then with the fingers of your right hand, thumb extended, you've got to point your fingers along R, palm facing F. And then push R on top of F with the fingers of your right hand. And your fingers and your thumb points directly away from you, i.e. directly into the screen, i.e. negative Z. Let me click this button up here that says show tau arrow to see the direction of the torque. It drew it anchored at the origin. And what is that symbol? Because notice it's labeled at tau arrow. It's down there at the origin. It's an X in a circle. That is the way that when you have a 2D view, you represent a vector that's pointing away from you, because it's supposed to remind you of an actual arrow like you would shoot from a bow. And if you look at one of those arrows from the back, you see the feathers crossed. And so you're looking at the back of an arrow. And that's representing an arrow pointing away from you into the screen, negative Z. Okay, so the direction is negative Z, negative K hat, for the given R and F. Does that make sense? All right. I'm going to take that away for the moment, and I'm going to ask us to think about another situation. If you'll notice, if I take hold of that crosshair at the end of the force vector, I can change both the magnitude and the direction of the force. And you can see the numbers for tau magnitude changing. So here's the question, first question. What orientation of F relative to R, what angle phi between R and F would give us a torque of 0? Think about that. Pause the video if you wish and then come back. Okay, what orientation of R and F, what angle phi between R and F gives us a torque of 0? Remembering properties of cross product, did you say that we need to have R and F along the same direction, parallel to each other? Because then phi is 0, and we're taking the sine of 0, and we're getting 0. I'm getting close to that here. Oh, and by the way, this animation, instead of calling the angle phi, it calls it theta RF. But that's phi. There's another orientation between R and F that would give me 0 torque. Not just phi equals 0, but what other phi? Did you say 180 degrees, like that? The reason the torque magnitude up there isn't exactly 0 is because I haven't got the force exactly opposite to R. But it would, if I could get it exactly, I'd get a torque of 0. All right, that gives me no torque at all. Okay? All right. Biggest torque would be if I get that angle between R and F at exactly 90 degrees. That'll give me the biggest torque. But here's a different question. What orientation of R relative to F, okay, how should I orient the two vectors R and F if I want to get the torque direction to be not negative Z, but just the opposite, positive Z, out of the screen towards us? And what I get to do this animation is change the direction and magnitude, but let's focus on direction, the direction of F. Think about that. Pause the video and then come back. I want to get the torque in plus Z out of the screen towards us. Did you say that all I merely have to do is put the force vector on the other side of R, like that? Anywhere on this other side, if you like the left side of R, will give me a torque out of the screen towards us. From the right-hand rule, practice it. Slide the R out along the black dashed line so that it has a common tail with F. Extend your right hand with the fingers along R, palm facing F, and then push the R on top of F. Your thumb points right towards you. So if I click that now, show tau, look at the picture. The tau arrow at the origin is a dot with a circle around it. Because now you're looking at an arrow coming right at you and you're seeing the point of it coming at you. Okay? So anywhere over here, see, I can keep the force anywhere to the left of R, and the torque is out of the screen towards me. Conversely, if the force is anywhere on the right side of R, anywhere on the right side of R, the torque is away from me. See the different symbol down there for the torque? Out of the screen, into the screen. Okay? All right, so that's more practice with the vector product. Now it's within the context of torque. One more tip about calculating torque using this new method of the vector product R cross F. Let's remember the useful version of the vector product if you're given the two vectors in unit vector notation. So now, what if you're given the position vector R and the force vector F in unit vector notation? So R arrow is given in that form. X times I hat plus Y times J hat plus Z times K hat, where X and Y and Z are numbers in meters. And the force F arrow is given in this form. F sub X I hat plus F sub Y J hat plus F sub Z K hat, where Fx, Fy, and Fz are numbers in newtons. Then, to calculate the torque in unit vector notation, use this lengthy formula, which comes from the lengthy formula I showed you in the previous video. Except now the specific vectors are r, f, and tau. Okay, so start with y times fz minus z times fy, all times I hat. So this quantity in the first parentheses is the x component of the torque, tau sub x, plus z times f sub x minus x times f sub z, all times j hat. So the second quantity in the parentheses is the y component of the torque, tau sub y, plus x times f sub y minus y times f sub x, all times k hat. So this quantity in the parentheses is the z component of the torque, tau sub z. Use that if you're given r and f in unit vector notation. Okay, I'm going to leave you on this video. We're going to do more practicing in class itself. But now I'm leaving you with a class engagement exercise where you will enter your answers on Blackboard. And it's practice with torque as a vector product, R cross F. And it's somewhat similar to the practice we did together on the previous video lecture. Here's what it says. We have three situations, A, B, and C, in which we need to determine the direction of a force vector F in order to produce a torque tau on a particle that points in a specified direction. So we've got a particle. It's got a certain position r relative to the origin O. Our goal is to get the torque on it in a specified direction. We're going to need to figure out which way the force has to point. Okay? In each situation, the position vector r of the particle extends from the origin along the positive direction of a z-axis to the particle. And you can see it. Here's the r vector in case A, and it's the same r vector in case B, and it's the same r vector in case C. The particle is the red dot. For each situation, state the required direction of the force F to get the torque. Now the torque is drawn in each picture. There's the tau in the first picture. Notice it points in negative x. There's the tau in the second picture. It points in negative y. And we'll mention the third case in a minute. So in each case, we have to tell you what direction the force points in. The answer for the force will be the positive or the negative direction of a coordinate axis. So I'm telling you that. The force will be either plus x or minus x direction, plus y or minus y, plus z or minus z in each case. All right, you have to tell me what's the direction of the F. In case A, the torque is in the negative direction of the x-axis. So what's the direction of the force? The force is acting on that particle. Case B, the torque is in the negative direction of the y-axis. So what's the required direction of the force F on the particle? Okay, case C is a little different. The torque magnitude is 0, but the force F is not 0. There is a force acting on the particle, but I want the torque to be 0. Turns out there are two possible answers. I want you to pick the one for the force vector that gives you a positive, that it gives the force vector in a positive direction of an axis. Okay, so in each case, you're going to say A, B, C, and you're going to tell me what direction the force on the particle points in. Okay, and that will be on Blackboard. And then we will practice in class on Wednesday, calculating torque as a vector product. That's all for this video.